In this unit, we're going to be talking about exponential functions. And in particular, this section is on exponential growth. Exponential functions are used in the real world in a lot of different ways. One of the ways that you might be able to best relate to exponential growth is through just money. So when you put money into an account, it will grow over time, and that will typically grow exponentially. Which we will see later on in different forms. Another way that we might see exponential growth is through populations. If you have a population of, let's say, mice on your field and they're not taken care of early enough, then you might see that those mice will grow and grow and grow to a point where it might even become unmanageable. So what we're going to do is we're going to look at exponential growth today, and we'll look at decay in the next lesson. So an exponential function is a function of the form f of x equals b to the x. This is a little bit different than, say, 2 x squared or 3x to the third, because we normally see x kind of in the base, and then our exponent is our 2 or our 3. Here, we might have 2 or 3 as the base, and then x as the exponent. So it kind of switches positions. So what I've got here is I've got 2 to the x and 10 to the x. And what we'll do is we'll take a look at just how these behave as x gets smaller or larger. Let's start at x is 0. So if I do 2 to the 0, this is 1, which makes sense because anything to the power of 0 is 1. So I can fill in 1 here, and I can actually fill in 1 over here as well, because if I do 10 to the 0, then I've got 1 as well. Okay, let's go in the positive direction. If I go 2 to the first power, I get 2, 2 to the second power, I get 4, and 2 to the third power, I'll get 8. So 2, 4, 8. Okay, what do you notice about that? Well, I see that it doubles here, and then it doubles again, and then it doubles another time. So this makes sense. 2 to the whatever just means 2 multiplied to itself that many times. So then, using that same logic, 10 to the first is 10, and then multiplied by another 10, 10 to the second is 100, and 10 to the third power is 1,000. So this is 10, 100, and then 1,000. All right, what about the other direction in the negatives? 2 to the negative 1 is 0.5. Now, if I turn this into a fraction, that's 1/2. What about 2 to the negative 2? That's 0.25. Again, if I turn that into a fraction, that's 1/4. And then 2 to the negative 3 is 0.125. If I turn that into a fraction, I get 1/8. All right, what do we notice here? Well, to the first power was 2. To the negative first power is 1/2. To the second power is 4. To the negative second power is 1/4. And to the third power is 8. To the negative third power is 1/8. I can reasonably assume that as this continues, the negative direction will just be 1 over whatever the positive direction is. Let's test that theory for 10 to the x. 10 to the negative 1 is 0.1, otherwise 1/10. 10 to the negative 2 as a fraction is 1 over 100. And 10 to the negative 3 as a fraction is 1 over 1,000. So it does seem like that holds true. Now, when I go to graph these, I get the following. On the left, I see 2 to the x. On the right, I see 10 to the x. And let's compare and contrast. What's the domain of each function? So remember, domain is the set of all x values. When I look at the set of all x values, this can go infinitely to the left and infinitely to the right for both. So I would say that x is from negative infinity less than x less than positive infinity. Okay, what about the range? It appears that I'm going to go down toward y equals 0, but I don't know that I actually reach y equals 0. So I would say 0 less than y less than, and then I can shoot upwards into positive infinity. And in what ways are these functions similar and which ways do they differ? Well, they both have the same domain and range here, but I see that 10 to the x is much sharper of a turn. This is going to grow much, much faster than 2 to the x. Okay, so I would say same domain and range, and even the same shape, or at least a similar shape, but 10 to the x will grow faster. So what makes it grow faster? Let's talk about some of the transformations that are taking place here. These transformations are the same as every other function that we've seen in standard form with these a, b, h, and k's. Remember that a represents a vertical stretch or compression. If the absolute value of a is greater than 1, the graph is stretched vertically. If the absolute value of a is between 0 and 1, the graph is compressed vertically. If a is negative, the graph is reflected over the x-axis. B is the base constant of the function, so that's the 2 or the 10. X is the variable component of the function, so that's just my x, g of x or y. G of x is my y. It could also be f of x. If negative x, then the graph is reflected over the y-axis. H represents the horizontal translation. So this is the shift of the function left and right. Remember that because it's horizontal, it's kind of the opposite of what I would normally think. If it's x minus h, then I'm actually going to shift to the right h units. If it's x plus h, then the graph is going to be shifted to the left h units. And finally, K represents my vertical translation. This is my shift upwards or downwards. Remember, vertical, this makes sense. This is intuitive. If it's plus K, I go up that many. If it's minus K, I go down that many. The next thing I'll need are the reference points and asymptotes. So I've got 2 reference points, as I had for my last functions that we worked with. I've got reference point 1 and reference point 2. Now, this time I don't have an initial point because it's not really starting anywhere, but my first reference point is going to be at h, comma, a plus k, and then my second is going to be 1 plus h, and then a times b plus k. I'm also going to have a horizontal asymptote. Remember, I saw that it didn't quite reach y equals 0. That's because there was a horizontal asymptote there at y equals 0. Well, there's always going to be a horizontal asymptote at y equals k. So the first thing I want to do is let's use these to find different transformations, reference points, and asymptotes for the given function. Let's start off with g of x equals negative 3 times the quantity 2 to the x minus 2, and then plus 1 at the end. Remembering that standard form is the following. G of x equals a times b to the x minus h, and then plus k at the end. So first identify a, b, h, and k. All right, a is -3. Okay, what does this tell me? This tells me that there's going to be a vertical stretch of 3, because the absolute value of -3 is +3. And there's also going to be a reflection. Okay, there's going to be a vertical reflection. And then b is 2. H is 2 as well. Now, because this is x minus 2, I'm actually going to move to the right 2. And then k is 1. So when I look at my first reference point, which is h comma a plus k, now that I've identified a, b, h, and k, I can go ahead and say that my first reference point is going to be 2, comma, a plus k would be -3 plus 1, which is 2, -2. And my second reference point is 1 plus h, so that's going to be 1 plus 2. And then a times b, so -3 times 2 plus 1 at the end. So this will be the same as 1 plus 2 is 3. And then -3 times 2 is -6 plus 1. That's going to make -5. And my horizontal asymptote is going to be at y equals k is 1. So what I would do is I would plot these 2 points. I would plot my horizontal asymptote, and then I would graph. We would see something similar to this. Let's do another one. 1.5 times 10 to the x minus 3, and then I've got -5 here. All right, a is 1.5. B, so this base is 10. H is 3. Remember that it's x minus h, so not -3, x minus 3. H is 3. And then k is -5. First reference point is h comma a plus k. So I'd say 3 comma 1.5 plus -5. Okay, so that's going to be 3, then -3.5. 1 plus h, so that'll be 1 plus 3, comma, a times b would be 1.5 times 10, and then plus -5. So this will end up being 1 plus 3 is 4, and 1.5 times 10, or 1.5 of 10, is 15, plus a -5 brings me back to 10. And y equals k is my horizontal asymptote, so I will say there's a horizontal asymptote at y equals -5. Again, I would plot these 2 points, I would draw in my horizontal asymptote, and then when I go to just find the curve, it would look something similar to this. It's a very sharp curve here. All right, so what we did was we took the function, and then using a reference point, a couple of reference points, and horizontal asymptote, I was able to find a reasonable approximation for the graph. The next thing is we're going to just do the reverse. So given the graph here, let's find what this function in standard form actually is. So it says use the graph to the right to find the exponential function of the form g of x equals a times b to the x minus h plus k given that b equals 2. So that's an important thing. We need to have a, b, h, and k. And here, b is already given to us as 2. So I just need to find what a is, what h is, and what k is. Now, luckily, I'm also told what the horizontal asymptote here is. That's y equals 1. That's important because there's always going to be a horizontal asymptote at y equals k. So if I know that there's a horizontal asymptote at y equals 1, then I can say that there's a horizontal asymptote at y equals k, y equals 1. Now my first reference point. Okay, so my first reference point, this is going to be negative 1/3, negative 1/3. Okay, so I always look for the one to the left. If I'm given 2, pick the one on the left. So if this is h comma a plus k, I already know that h is negative 1/3. Okay, if I want, I can box these in and find them easier later. So I can say here, this would be k equals 1. Then h equals negative 1/3. So I've got b, h, k. I just need to find a. All right, then I know a plus k equals negative 1/3 as well. And since I found earlier k equals 1, then I can say that a plus k is 1. This is equal to negative 1/3. And subtracting 1 from both sides. Okay, here I'm going to have to think of this as subtracting 3/3 from both sides. This will get a equals negative 4/3. Okay, now I know what a is, what b is, what h is, and what k is. I can go ahead and fill this in. My standard form is g of x equals a, so g of x equals negative 4/3 times b is 2 to the power of x minus h, so minus negative 1/3, or I'd say plus 1/3, plus k at the end, so plus 1. All right, let's do one more of these. Oh, actually, it looks like I'm just going to go right to a modeling problem. So it says exponential growth functions can be modeled by f of t equals a times 1 plus r to the t, where a is greater than 0 and r is the constant percentage increased. This is going to be oftentimes expressed as a decimal for each unit increase in time. A is the principal amount or the value at which the item's worth begins at. R is the growth rate, and the base of the exponent 1 plus r is called the growth factor. Okay, so how do we use this? Here it says a rare guitar is purchased for $12,000. So that's my principal amount. That's what it starts at. Now it might have been cheaper than that at one point, but for me, I bought it at $12,000. So that is my starting amount. That's my principal amount. Experts estimate that the value of the guitar will increase by 14% each year. Find the exponential growth function that models this and use a graphing utility to find when the value of the guitar will reach $60,000. Okay, so f of t equals a times 1 plus r to the t. The principal amount, what I bought it at, is $12,000. The growth rate is 14%, so what I need to do is do 14 divided by 100, because it's 14 out of 100%. And I see that r is going to be 0.14. So when I put this together, I will get f of t equals 12,000 times 1 plus 0.14 to the t. Now I want to know when it's going to reach 60,000. So what I would do is I would put this function into a graphing calculator or Desmos, and then I would also put y equals 60,000, and then I would just find when those two intersect. Here, I see that it intersects at 12.29, which tells me that this guitar is going to be worth $60,000, quite a bit more than what I paid, $12,000, in just a little over 12 years. So we can see the power of exponential growth and how putting a little bit of money away towards some investments, good investments, may be well worth it in the future.